welcome back. We will continue our discussion on the atomic structure as part of our electrochemical technology for pollution monitoring. Yesterday we had seen this figure where I had explained to you that the origin of the hydrogen spectra arises from the fact that electrons from higher energy levels will fall to the lower energy levels after excitation. So, we have a Lyman series, we have Balmer series when the transition takes place from n is equal to 2, and then Paschen series when n is equal to 3, 3, 4, 5, 6 etc. excitation can take place. And then we have bracket series and Fund series. Now, we also want to know a little bit about the Summerfield theory. In 1916, Summerfield modified Bohr's theory to include elliptical orbits instead of stationary orbits, circular orbits. So, circular orbits form only a part of a special case of elliptical orbits, because elliptical orbits have two axes A and B. When A is equal to B, we have a circular orbit. So, the velocity of an electron moving in an orbit will be greatest when it approaches closest to the object, that is nucleus, and least when it is farthest. So, this introduces variability in the orbit also, which as a whole will precess around the nucleus. Okay. This precessional movement will result in small energy changes, and that will be reflected as fine structure in the spectrum. So, this is how the spectrum of hydrogen could be explained at that time. And Summerfield concept permitted the subdivision of the Bohr stationary states of slightly differing energy levels corresponding to differences in orbital shapes. So, this is the basics of modern concepts of electronic configurations. Further, it projected the possibility of penetrating orbits, because most of the orbits are spaces. The one orbit, if it is empty space, an orbit can occupy another one into one another, and then the spaces can also, electron can be in any of these orbits. So, the probability of electron being in a particular space around the nucleus is always positive, and it projected the possibility of penetrating orbits. Therefore, certain electrons may penetrate closer to the nucleus than others, then permitting qualitative pictures of the more complicated atoms can be visualized. So, that was the idea. Now, look at this figure. This is the first one, that is circular orbit, that is Bohr's orbit, special case of elliptical orbit, and this is 2s and 2p. See how the orbits can be overlapping one another in this case, and here you can see there is lot of overlapping, various subshells for the electrons are there, and then this is rosette path of an electron. Electron can be moving in different orbits at different angles, different speeds, but only around the nucleus, and this is the Summerfield atomic model. So, how do the electrons then move around the nucleus? Because if the electrons are orbiting around one another, then the problem is how do you visualize an electron moving around a nucleus in different orbits at all. So, we have certain rules which were observed and which have been formulated for our better understanding. So, one is the rule of 8, that is inert gas atoms with the exception of helium, they contain 8 electrons in the outermost orbit. So, that is the rule of 8 except helium. Then helium, neon, argon, krypton, xenon and radon, they contain 2, 10, 18, 36 and 54, 86 electrons and represent the end of various horizontal series of the periodic classification. C.R. Burry postulated that maximum number of electrons in the various shells are 2, 8, 18 and 32, not more than that. Obviously, the total number of electrons will exceed the known elements. The maximum we have electrons in any element is about 108 elements are there, 108 electrons in a maximum. So, he also stated that no shell can contain more than 8 electrons unless another shell further removed from the nucleus is being formed. So, this concept permitted logical explanation for the configuration of the transition and inner transition elements, that is filling up of inner electronic configurations of the electrons. So, for example, here you can see that helium has got 2 electrons, atomic number is 2 and it has got 2 electrons in the K shell, and next is neon, it has got 10. So, 2 go into K shell and 8 goes into L shell. Similarly, argon 2, 8, 8, krypton 2, 8, 18, 8, xenon is 2, 8, 18, 18, 18, 8, radon is 2, 8, 18, 32, 18, 8, like that the electronic configurations of the electrons in the inert gas. Okay. Now, suppose there is one element which is lower than radon. So, it will have 7 electrons in the last outermost orbit. So, that would be something like halogen group. Okay. So, we can understand the periodic tables very easily. So, here is hydrogen atom electron orbitals for magnetic number m is equal to 0 and n is equal to 1, n is equal to 2, n is equal to 3 we have, and this is a pictorial representation and quantum designations. So, if there are only so many electrons, we should be able to designate every electron by its own description. So, how do we do that? The Bohr-Summerfield concept of electrons revolving around the nucleus, atomic nuclei, is limited to well defined shapes only. It is essentially a rough pictorial presentation. Modern concepts based on the wave mechanics depict quantitative comparative density of the electronic charges at any given point within the atom based on the theory of probability. So, we essentially say that the electron remains maximum in this space of space around the nucleus. If it is K shell or if it is S orbital, it will be in a space around the nucleus in the circular orbit space. So, similarly, if it is a p orbital, electron in a p orbital, the object will be something like a dumbbell shape. So, this dumbbell shape also we can say the probability of electron being present in that dumbbell shape is maximum at any time. Like that we can continue. So, essentially this means that electrons will tend to group themselves in a series of positions relative to the nucleus, which may be considered as energy levels. With respect to nucleus, if it is nearer the nucleus, energy level will be very high. If it is removed farther away, energy level will be lower. So, we have a series of energy levels, which does not mean that the electrons are farther away, in the space. No, it will be in the same area, but grouping is more, charge density will be more. So, transitions can be permitted only between these energy levels, giving rise to a spectrum. That is what spectroscopy is all about. So, the electrons are best described in terms of 4 quantum numbers, that is principal quantum number n, orbital quantum number is L, magnetic quantum number is m, spin quantum number is s. So, with these 4 orbital magnetic quantum numbers, we can define any electron in a given system, that is in any element. So, the energy levels corresponding to different orbital levels n, different orbits are given by this equation, and W is equal to 2 pi square z square. This is all PUC stuff, okay, PUC chemistry stuff. I am not going into details because this is only to remind you of the things as they are with respect to understanding of the atomic structure. We do not need many of these information, but it is for the sake of brevity we are doing it. So, here this equation represents the energy in at any particular this thing. Here we have W is energy of the electron and Z is the total number of electrons or atomic number, E is the electronic charge and mu is the electronic mass, H is Planck's constant. All those things are very well known, and the energy of a particular level can be calculated simply by putting N. All other things are constant. This is known as Rydberg's constant. So, basically what does it mean? W represents the mean distance of the electron from the nucleus. So, the principal quantum number may have value from n is equal to 1 to infinity, where infinity refers to the complete removal of the electron from the system. Suppose you have one nucleus and one electron, take it to higher energy levels, and then when it is completely removed, n it becomes infinity. So, production that results in the production of an ion, because the electron is completely gone. So, they may be designated. So, the electrons may be designated as being in K shell, L shell, M shell, etc. So, the last electron that can be transferred to higher energy levels until it is produces an positive ion. So, the orbital quantum number L is a measure of the orbital angular momentum of the electron. This is another way of describing the electron. So, there are L values of L varies from 0 to n minus 1. So, when n is 1, L value is 0, n is equal to 2, L will be 0 and 1, n is equal to 3, again n minus 1 means it should become 0, 1 and 2. Like that there will be orbital angular momentum, that also can be described as the described for determining the energy of an electron. So, one is principal quantum number, it says where the electron is, next is its angular orbital angular momentum L quantum number. Then we have these things are customarily named after spectral terms, namely S, P, D and F. So, electrons present in these orbitals are referred as SPDF electrons also, and the orbitals are also called as SPDF orbitals. So, we have a third quantum number, that is magnetic quantum number. So, what happens is when some spectral lines are there, you put the sample in a magnetic field, the spectral lines split. So, the orbital angular momentum undergoes a precessional movement and describes a cone about an axis in the direction of the field of the magnitude, of which is given by ml into h by 2 pi. Here you can see in the slide, I have written it in the last line, the orbital angular momentum is ml h by 2 pi. So, we have magnetic number quantum number, it can be from L to minus L to plus L. So, for S electron, L should be 0 and M should be 0, and P for a P electron, L is equal to 1 and M should be, magnetic quantum numbers should be minus 1 to plus 1, that is minus 1, 0 and plus 1. Similarly, L is equal to 2 will result in minus 2, minus 1, 0 and plus 1 and plus 2. For F electrons again we have about 6 magnetic quantum numbers, 7, L is equal to 3. Then we have a spin quantum number. This refers only to the spin of the electron, whether electron goes clockwise or anti-clockwise. Just like any planet, electron is also supposed to precess around itself while it is going around the nucleus. So, that spin quantum number is given by this expression h into square root of s into s plus 1 divided by 2 pi, where s is equal to half or minus half. This is a sort of arbitrary number, and it depends upon whether it is precessing along the magnetic field or opposing them. So, it is for each value of m there are only two different s quantum numbers. So, no two electrons within any atom can have all the same 4 quantum numbers. This is known as Pauli exclusion principle. So, each electron differs from every other electron in a given atom in its total energy. So, knowledge of the exact order in which atomic orbitals are occupied is based on the interpretation of atomic spectra in terms of how the spectral lines result from the permitted electronic transitions. So, what we are essentially saying is how the electrons are occupied will reflect on the spectral lines. So, you inspect the spectrum, you will know how the electrons are occupying different energy levels. Heavier atoms have very complicated spectral patterns and overlaps occurring in similar systems. This is expected, is not it? So, here is a small pictorial representation of the orbitals. This is s orbitals, completely spherical, p orbital dumbbell shaped. These will be in x y direction, and then one may be y z and x z. 3 different p orbitals can be there, and d orbitals are 2 dumbbell shaped in x y plane and other planes also. So, f orbital is something you can imagine a hexagon, like you can imagine a cube, a nucleus at the center, 4 at the top occupying the 4 corners, and 4 orbitals at the bottom, all are dumbbell shaped only. Okay? So, except spherical the s orbitals. So, this is px, py and pz orbital. These are all very simple stuff, and the actual energy level diagram will tell us that first one is whenever we want to put the electrons in the atomic structure. If I want to write down, first I have to fill 1s and then 2s, 2p, 3s, 3p and then 4s, afterwards 3d. See, there is a slight this thing, energy level of 3d is higher than 4s, and then 4p, 4d, 4f etc. This is the typical energy level diagram of an of the electron filling in the nucleus. So, if I use this a spiral figure, you will get N, L, 1s, 2s etc. This is how the electrons are filled. This is part of the PUC textbooks only. You will find this figure and explanation etc. in the PUC this thing. With based on this type of electron filling, we have the modern periodic table, and here we have the hydrogen is here, and then helium is here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon, and then we have the second periodic second period. These are all red ones are called here they are alkali metals, here it is transition metals, here it is alkaline earth metals, beryllium, magnesium, calcium, strontium, barium. The orange ones are all alkaline earth metals. Here we have couple of post transition metals, and they are cadmium, zinc, mercury, and here we have noble gases on the right hand side, and then the things depicted in blue are halogens, all others are, these are all non-metals, and some of them are metals and non-metals together. So, these are all post transition, these are all semi metals, metalloids they are called, and then we have where 3D and 3F, 4D etc. those things are filled. We have the transition metals, and 4F and 5F are called lanthanides and actinides. So, this is how so many elements we have up to the whole periodic table has been organized, and it is easy for us to work on this understanding of the current level of the arrangement of the electrons and nucleus and neutrons in the elements, and how the elements can be organized in different fashions. Okay. So, that completes our discussion about the basic structure of the atom. So, what we have said essentially is an atom is composed of protons, neutrons and electrons. There are other subdivision of particles smaller than electrons. They are all known as positrons, mesons, etc. Some of them have independent existence, some of them do not have. They are all existing momentarily, maybe in nuclear reactors and stars. So, what we need from this introduction is that we need the outer electrons for our discussion in the electrochemical technology. That is why I have given you this. So, that will enable us to proceed for the next module, that is properties of solutions. So, why do we do properties of solutions first? The idea is most of the electrochemical systems are all aqueous and non-aqueous systems containing water and non-aqueous solvents also, methanol, ethanol, etc. And we should know how the ions or metal ions behave in the aqueous systems and non-aqueous systems. Okay. So, here we have most of the this is sort of introduction. Most of the electrochemical techniques are concerned with reactions in solutions. Occasionally gaseous state, definitely yes. And in normal life we rarely come across very pure substances in solutions. Most of the solutions contain molecules, atoms, ions and mixtures, etc. Since we will be dealing with solutions, it is desirable to know about the properties of the solutions. In addition, we need to know how to express the concentrations of solutions in various units, because without no capability to express the concentrations, we will be nowhere. In this context, let us learn about the definitions of some relevant terms related to solutions. So, what are the terms? Here first I defined a solution. What is a solution? Solutions are homogeneous mixtures of two or more components. Largest quantity present in a mixture is known as solvent, which determines the physical state in which solution exists. So, we know what is solution, what is a solvent. We define solute. So, what is a solute? Solute is an invisible component in a solution that is dissolved, not visible to us. They are called as solutes. We can call binary solute, tertiary solute, quaternary solutions, and they all types refer to the different types of solutes present in the given solvent. So, one solvent can contain number of solutes, giving rise to binary, tertiary, quaternary and several other mixtures also. So, that is a solute. They should be dissolved, they should not be visible to naked eye. And then we have gaseous solutions. They contain gas or liquid or solid solids. So, liquid solutions may contain gas or liquids or solid solids. This we understand very easily, is not it? Liquid solutions may contain gas, gas may be dissolved. All our fishes in the rivers live because there is oxygen gas in the water, in the river, in the lakes, in the sea. So, liquid solutions may contain gas, it may be contain another liquid, or it may contain a solid also. Solid solutions may contain gas or liquids or solid solutes, other way around also is possible. So, but we call them solid solutions. If a solid contains another solid, then it is a solid solution. If it contains gas, solid solution. If it contains liquid, again solid solution, and the solid solutes it may contain also. So, how do I express the concentration of the solution? Here is a very simple way of expressing mass percentage. So, what is mass percentage? Mass of the component in the solution divided by total mass of the solution into 100. Very simple explanation, where I say 5 gram is dissolved in 100 gram of the solution. Okay. Multiplied by 100, you can call it mass percentage. Total mass present in a solution divided by total mass of the solution, and component means solutes. 5 gram of sugar in 100 gram of water, or 50 gram of sugar in 10 ml of 10 gram of water. That is also the, so we can have any number of expressions, but standard expression would be in percentage multiplied by 100, that will give us mass component of a mass of a component. I can also say volume component, volume of the component. If it is a liquid, I cannot say so many grams of the liquid is present in so many grams of the solution. I can instead as well say that we can, it contains 10 ml of the component A and 10 ml of the component B in 100 ml of solution or 10 ml of solution. So, multiplied by 100, we have a volume percentage of a component. This is another simple way of expressing. We come across in electrochemical technology all these terms very regularly. That is why I wanted to remind you. Then third is mass by volume percentage, that is number of parts, number of the mass by volume percentage, mass of the solute dissolved in 100 ml of solution, that is the mass by volume percentage, third one. So, fourth one is parts per million, number of parts of component divided by total number of all components in solution multiplied by 10 raised to 6. That means, if there is one part in 10 raised to 6 part of the all the components, then it is known as 1 ppm, 1 microgram per milliliter or 1 milligram per liter. They are also equivalent concentrations. So, I can say either 1 ppm or 1 microgram per liter or 1 milligram, 1 microgram per ml or 1 milligram per liter. You can say 1 kg in 1 ton also, something like that. That is also possible. So, parts per billion level is another very specific term people use, that represents number of parts of component divided by total number of parts of all components in solution multiplied by 10 raised to 9. So, if there is one part in 10 raised to 9 solution, then you call it 1 nanogram. Okay. So, 1 ppb, parts per billion, 1 ppb is 1 nanogram per ml of the solution. So, we also have parts per trillion, ppt. So, we express many of our pollutants in these terms. Number of parts of a component divided by total number of parts of all components multiplied by 10 raised to 12. Below that also is possible, that is known as femtogram, but we will not worry about it, because most of the time we will be using either percentage, mass by volume, mass by mass, moles, number of moles per liter, parts per million, parts per billion, or parts per trillion, not more than that. So, we also should know what is known as mole fraction of a component. So, what is mole fraction? It is defined as x. We can call it anything, there is nothing sacred about x. So, number of moles of a component divided by total number of moles of all components, that is x A it should be referring to the number of components of A divided by number of other components Na plus Nb plus Nc. If there are more number of components, more. So, we can write, we normally write it either like this, Na over Na plus Nb, or simply mole fraction x1 or chi1 is equal to N1 divided by sigma N1, total number of components at the bottom. So, we also have another one, that is molarity. So, molarity is number of moles of the solute dissolved in 1 liter of the solution. So, what is a mole? It is the molecular weight of a substance dissolved in 1 liter. So, if I take sodium chloride, it is sodium is 23 atomic weight and chloride is 35. So, 58 grams of sodium chloride dissolved in 1 liter of water gives you 1 mole of sodium chloride. So, in terms of expression, if I want to write an equation, then I should say moles of the solute divided by volume of the solution, and that should be in liters. It cannot be in milliliters or something. This is another way. Okay. Then we define another term, that is known as molality. In molality, what we do is moles of the solute divided by mass of the solvent in kg. The only difference between this and previous one is volume of the solution here, volume of the solution in 1 liter, correct. So, the next one is molality, refers to moles of solute. Here also it is moles of solute only in molarity, but here denominator differs. Volume of the solution in gives you molarity, and mass of the solvent in kg gives you molality. So, mass percent, mole fraction and molality are independent of temperature, whereas molarity, weight by volume percent, are all functions of temperature. Okay. So, you can see that as the temperature increases, solubility also increases sometimes. So, they are all functions of temperature, whereas mass percent, mole fraction and molality, they have no influence by temperature. Pressure, of course, it does not arise, because 99% of the solvents are not incompressible, they are incompressible. And then we define another term, that is known as solubility. Solubility of a substance is defined as the total quantity of grams of the solute dissolved in a unit quantity of the solvent at a given temperature and pressure. Essentially, what the definition may look very big, but actually what it means is the quantity dissolved in a unit quantity of the solvent at a pressure given temperature. That is how we define the solubility, because solubility is a function of temperature and pressure, especially if it involves gases, it involves pressure also. So, a solubility is something like an equilibrium reaction. Here I am showing here solute plus solvent is equal to solution. I have written it at the bottom. So, it is an equilibrium reaction between the dissolved salts and excess solute present in the solution. So, when a solid solute is added to a solvent, some solute is dissolves and its concentration increases in the solution. This process is known as dissolution. Everybody knows this. Some solute particles collide with solute solid particles and get separated out of solution. This process is known as crystallization. Since both these processes occur all the time, a stage is reached when both these processes occur at the same speed, at the same time. Then we have an equilibrium described as solvent plus solute is going to solution. Okay. At a given temperature, pressure maximum concentration of the solute is in dynamic equilibrium with undissolved solute, that is called as saturated solution, maximum dissolved. And you keep on adding sugar to water, it keeps on dissolving, and after some time the sugar will not dissolve. So, sugar will remain excess as solid only at the bottom of the beaker. So, then we call it saturated, it cannot dissolve anymore. So, an unsaturated solution can dissolve more solutes to become saturated solution. A polar substance like sugar, salt, etc., they dissolve in polar solvents easily. A non-polar substance dissolves in non-polar solvents. So, we say like dissolves like, and many gases also dissolve in solvents including water. We will continue our discussion in the next class. Thank you.